Great. Hello, everyone. This is Xibei from DoraHacks. Thank you all for joining us today for the workshop series of the DoraHacks Starship Use Cases Hackathon. We have a special guest with us today, Dr. Joseph Parker, the Chief Science Officer at Terran Space Academy, will be presenting a workshop on Magnetoplasmadynamic thrusters and Magnetoshell shields. I'm very excited to be able to hear his insights on this topic, and I'm pretty sure everyone who's watching this episode today will have some great takeaways as well. Before we kickstart this session, let me just give you a quick introduction about who we are and just an overview of our Starship Use Cases Hackathon. So for those of you who don't know DoraHacks quite well enough yet, we are a global hackathon organizer and one of the world's most active developer incentive platforms. We love to support innovation in blockchain, quantum computing, space tech, and more. And we provide a wide range of toolkits to help developers around the world team up and fund their ideas and projects via hackathons, grants, bounties, etc. And as we are very much committed to supporting innovators within the space sector, apart from our ongoing long-term space resources and exploration grant program, we launched another bigger initiative to foster space tech innovation at the beginning of this month, which is our Starship Use Cases Hackathon, with $100K in prizes. Capitalizing on the potential offered by Starship, we have developed 18 use cases and 2 open challenges for hackers. Use cases include space-based farming, routers for global Internet of Things, metals from the moon, etc. 2 open challenges are novel satellite constellations and recreation facilities for space hotel. So through this hackathon, we like to motivate all space enthusiasts with engineering skills to build their solutions for space. You can check out the link below in the description. There you will find more details about this hackathon, including background and task description for each use case, hacker resources that our team has curated for you to enhance your solution design, and also the updates about more upcoming workshops. The submission portal is already open, so you can join the hackathon now, and we can't wait to review all your submissions. Lastly, for the audience, during the workshop, please feel free to share any questions you have in the YouTube chat room. I'll make sure to ask Joseph your questions at the end. Now, without further ado, I'm excited to pass the mic to Joseph, and welcome, Joseph. Thanks so much for joining us today. Feel free to kickstart this session by giving us a brief introduction about yourself, about Terran Space Academy, before diving into the workshop content. Feel free to start.
Thank you. My name is Dr. Joseph Parker. Before I started in the military and I served in the Marine Corps for a while, and then the U.S. Air Force. In the Air Force, I became an ICBM commander with the Intercontinental Ballistic Missiles, Minuteman IIs, and served with Strategic Air Command, and then that became U.S. Space Command. And I started working on a master's degree in aerospace engineering at that time, and then actually got accepted into medical school. So I have a medical doctorate. And then after I had finished that and had things had slowed down a little bit, I went back and finished a master's degree in aerospace science, and I have a certificate in astrobiology. So I love everything space and have for quite a while. So I did my research thesis in radiation exposure, human radiation tolerance and expected exposure during colonization of the moon and Mars. And that kind of ties in with the need for a faster propulsion system than most spacecraft have right now.
Great. Thank you for sharing more about yourself. And what about Terran Space Academy? Can you speak a few words about the channel?
Absolutely. When I started studying space, there were 2 levels, either so simplistic that once you watch one of the videos, none of the rest really teach you anything new, or so complicated that they were for a tiny niche audience and there were perhaps, 30 or 40 super technical people working on that specific propulsion system that would understand it. We wanted to make something in the middle, something where someone with no prior space knowledge could listen to and learn something. So our lessons usually start kind of with a primary background for everybody, and then they get more technical so that, and we put the equations out so that people can follow them and learn to do them themselves, which is really kind of our hope, to be more of a trade school for space, right? Not everyone has the time to spend 4 or 8 years getting a space degree. You shouldn't have to, because space is going to need everyone. It'll need teachers, horticulturists, miners, and you can't send everyone. Everyone can't have their PhD in space science that's going to be going to the moon to build the colony and all that.
Great. Great to hear that. That's why I personally love Terran Space Academy videos so much. Yeah, feel free to start today's workshop then.
Sure.
I'm very excited to hear your insights on this this fascinating topic.
This really started, or the most important factor when we talk about colonizing the moon or Mars. I think the moon is a much better target initially. Mars is much further away. You've got all kinds of problems, whereas the moon, a lifeboat can get you back to Earth pretty quickly. When we talk about colonizing space, our first concern must be radiation exposure. The average radiation exposure here on Earth is usually no more than 2.5 millisieverts per year. And that's somewhere where there's a lot of radiation. Like there's a place in Iran where there's a lot of radon gas. There's one in Brazil where there's a lot of radioactive elements in the soil. So 2.5 millisieverts is something to keep in mind, because then you can realize on Mars, it's 250 millisieverts. So it's 100 times more. But then on the moon, it's 500. So it's twice the exposure that you get on Mars. In empty space, it's about 750 if you're unprotected or in a thin capsule. The Apollo astronauts survived going to the moon because they did several things. They went through the Van Allen radiation belts at its thinnest spot, which is called I think the South Atlantic anomaly. They went through extremely fast, and they didn't really know that much about radiation exposure. And it turns out that a solar storm would have actually killed one of the Apollo crews had they made it back a little later. Had they been extended another day and were coming back, a solar storm would have cooked them. So when we're talking about colonizing the moon and Mars, we're talking about needing to get places quickly to limit our exposure, because we get the most radiation exposure during our travels. So if you're going to Mars, you're getting 750 millisieverts on the way there, and that's like a 9-month journey if you go with chemical rockets. So then we get to the speed that something can move at, that our spaceships can move at. All chemical rocket engines they use combustion to produce a high temperature, and they're all about the same, because our materials right now can survive about 3,000 centigrade, or 3275 Kelvin, about the same. So that's the hottest we can keep them from melting. So the temperature is all the same. Their performance depends upon what you're throwing out the back. So when you have a set thermal temperature, and then the kinetic energy of each of those subatomic particles as it exhausts out the back determines the efficiency of your rocket engine. So the smaller something is, the faster it will go for the same kinetic momentum. So that's why the most efficient rockets use hydrogen fuel. All right. So if you're burning kerosene and you've got water and carbon dioxide being made, it's maybe your specific impulse when you're leaving the Earth is 279. If you're using hydrogen, or methane, it's 330, then hydrogen might be 350. When you get into space, it's much better. Hydrogen goes up to 450, while methane tops out at 380 seconds, and then RP1 probably around 320 or something like that. So we need more efficiency, and we're limited in how hot we can make these rocket engines. So then we started looking at ion engines, ion propulsion. So ion propulsion is where you strip an electron off a subatomic particle so that you can maneuver it with electric or magnetic fields. and you throw it out the back at high speed. Well, it turns out that for our ion drives, they can throw everything at about the same speed, so they're not limited. It's the opposite as chemical engines. If you can throw everything at the same speed, then you want to throw a bowling ball instead of a ping pong ball so that you get more momentum going out the back. And that's why you'll see ion engines using xenon. So xenon is the heaviest radioactive noble gas. Noble gases are easy to ionize, so you don't have to use a lot of energy. And xenon's the heaviest one. So everyone would like to use xenon, but it's rare and expensive and all this. So then you'll see some of them use krypton. So SpaceX used to use krypton in their Starlink satellite system. But then you'll notice they switched to argon. Now, argon is interesting because it's a noble gas. It's available for ion drives, and it's available on both the Earth and Mars. It's 1% of both atmospheres, though the Martian atmosphere is 1/100th as dense as the Earth. So 1% of 1/100th, you're getting to pretty thin. But you can still get argon on Mars. So then you start looking at your different ion thrusters and which one is going to work best. Ion engines were created a long time ago, and the first ones, I believe, were flown by the Soviets using cesium. And you can use metals with this. Some use iodine, some use lithium, and the lithium vapor has the best performance. But when you're talking about actually colonizing the moon or Mars and traveling back and forth and having a lot of transport, you need something that you can have access to. You need xenon. You're not going to be finding on the moon. And also the ion thrusters have a problem. The amount of thrust produced by your rocket is determined by two things: the exhaust velocity and your mass propellant flow. So what is the mass of propellant that can flow through your engine times the velocity it's going out the back? And for modern ion drives, that's a big problem because they're throwing things out at tremendous speeds. So like 50,000 meters per second is possible. Whereas gases coming out from a chemical engine don't go higher than 4,500 meters per second. So you're looking at 2 orders of magnitude better. And you say, that's great. Why don't we use them to get off Earth and go into space? Well, they can only process a few micrograms per second instead of kilograms per second. So to put that in perspective, a space shuttle main engine, I think it processes about 500 kilograms per second of propellant. Now, it might be 300 for the space shuttle, about 500 for the Raptors, and about 1,500 for the F1 rocket engines that were on the Saturn V's. So how much propellant mass you can process through your engine? Well, the ion drives can only process a tiny amount. So we need to create an ion drive that can process propellant at a fast enough rate, but still have a high enough performance so that we get both high efficiency, so we don't have to have 99% of our ship being fuel, or propellant rather, and you need high efficiency and pretty high thrust so it doesn't take us forever to get somewhere. If you launched me into orbit with a Starship and I had a xenon ion thruster, a gridded ion thruster, a regular ion thruster, it would take me about a year just to get up to good velocity, just to get up to the velocity that the chemical engines can get in a few minutes. So that's no good. You don't want human beings taking 9 years to get to Mars. So you've got to have high thrust at the start and high efficiency for the rest of your flight. Then you have to turn around and slow down unless you're going to aerobrake. And even if you're aerobraking, you have to be captured by the planet's gravity or the moon's gravity. So then we were looking at ion thrusters and saying, is there one that can process propellant pretty fast? And there are the 2 most popular types of ion, well, 3 most. There's a gridded ion thruster. You ionize your gas, you put an opposite charge here on this grid, you release the gas is attracted to the grid, and then that grid has holes in it, so the gas goes through, and then that streaming particle thing gives you propulsion, and every reaction, there's an equal and opposite reaction, and the ship starts moving. So gridded ion thrusters. Then there's Hall effect thrusters. where you use a magnetic field to ionize your gas and then an electric field to throw them out. And they're very popular, and a lot of things have that. And again, the SpaceX Starlink satellites, that's what they're using, is an argon Hall effect thruster. Then we have something called magnetoplasmadynamic thrusters. They are the opposite of Hall effect thrusters. Instead of using magnetic fields to ionize and electric fields to throw them out, they use electric fields to ionize and magnetic fields to throw them out. So that it's the Lorentz force that actually throws the particles out. So they're also called Lorentz thrusters sometimes. And these, it turns out, can process a pretty good mass propellant flow. They can process enough mass that instead of just getting micronewtons or millinewtons of force, they can end up getting 200 newtons of force. Well, that's enough to start doing something. 200 is not a bad number. Then the second thing with the magnetoplasmadynamic thrusters is, and they're very simple to build, by the way. I built one at home just for the fun of it and used helium gas, and it worked great. I put it in an acrylic shell, and you could watch the thing work. You need a 100 kilovolt transformer, by the way, which you have to be careful with. It doesn't have a lot of amps, but it will arc. So these aren't complicated. And then you can augment them with an external magnetic field. So there are sort of plain magnetoplasmadynamic thrusters, and then applied field magnetoplasmadynamic thrusters. So when you put a big magnet around them, you dramatically increase their performance. So companies have been looking at doing this, and one of the problems was that the electromagnet was so huge that it took a lot of power and it added a lot of mass. So a company in Germany called Neutron Star Systems started looking at using superconducting magnets. Now, superconducting materials have gotten to where they can operate up to liquid nitrogen temperatures. So if you're using a cryogenic fuel, and that would be liquid hydrogen, liquid methane, right? Those would be the two main ones. Then you can cool these magnets down with your fuel, just like you cool the rocket engine down to keep it from melting. You run the fuel through the engine to absorb the heat and keep the rocket engine from melting before you put it through the engine itself. And all modern rocket engines, except very simple ones, do that. Unless they're deep in space, sometimes they use radiative cooling. But almost all of them use what's called active cooling. So you can do that with these magnets too. So if you're using, say, now methane, it turns out, is a really good propellant for a magnetoplasmadynamic thruster. So picture a starship going up into orbit, refueling once, and then using magnetoplasmadynamic thrusters to get it on out to Mars. Now from 9 months, you've cut the travel time to 3 months. And back and forth to the moon would be faster also. And also the amount of mass of your ship that must be propellant is cut dramatically. So if you're using hydrogen, maybe 95% of your ship will need to be propellant when you leave Earth. If you're using, if you could use an ion drive with enough thrust, maybe only 25% of your ship would need to be propellant, and that leaves a lot of more mass when you get to where you're going. So if you've got a 100-ton ship that's using chemical engines, it might only get 5 tons to where it needs to go. If you've got one that's using ion, it might get 75 tons to where it needs to go. So it's much better. Now, using ion thrusters to get off the Earth is impossible right now because we don't have enough power, and that brings up another problem. Regular chemical combustion rocket engines create their own power. When you burn the hydrogen with the oxygen, you get heat, and that heat can be used to, that's the energy you use to throw the particles out the back. But with ion drives, you don't have combustion. There's not a combustion chamber, nothing's burning. You've just got a gas that you're applying power to. So let's look at the Vasimir engine by Dr. Cheng Diaz down in Houston. So he's got cold gas, and it goes into one chamber, and you hit it with radio waves, and you ionize the gas. Then you can control it with magnetic fields, and you put it into a magnetic bottle, and you hit it with more radio waves of a different frequency, and you heat the gas to millions of degrees, hotter than the surface of the sun, much hotter. And then you can open a little weakness in your magnetic bottle, and those particles go flying out, and you can try to accelerate them with magnetic fields. And now you've got the variable specific impulse magnetoplasma drive. So you end rocket engine, so Bessemer. So you end up with a very fast rocket, but you were putting that power in. So where do you get the power to run your radio waves and your magnetic fields that you're generating? Well, for most satellites, you use solar because they're very tiny and they don't mind going slow. But when you've got people on them and you're talking about big ships, you need a lot of power. Solar is not viable for this. It is not practical to build solar arrays big enough to propel a human ship toward Mars with ion drives. It just doesn't make sense. So now we're talking fission or fusion nuclear. A lot of people are working on fusion, but we don't have it yet. So let's look at fission. So you've got a nuclear reactor like the Soviet Topaz reactors, and you're revving them up and generating thermal energy, heat, and electrical energy, megawatts of electrical energy. Now you're talking. Now you can pump that electricity into your ion drive and get a very efficient, very fast form of propulsion. So when you have a nuclear reactor, you can run coolant, you can run propellant through it and heat it up. And that's what the NERVA engines did, developed by the United States. They ran hydrogen, liquid hydrogen into these reactors. The hydrogen would heat up and go flying out the back. They're twice as efficient as chemical rocket engines. So the Space Shuttle main engines had a specific impulse of 455 seconds. That's how we measure specific impulse or rocket engine efficiency. The nuclear thermal would be 900, twice as good, right? But if you take that nuclear energy and you turn it into electricity and run that through your ion drive, now you're talking about 5,000 seconds of specific impulse. So at least 10 times better with a magnetoplasmadynamic thruster. Now the MPDs don't throw things out the back as fast as some of the other ion engine designs, but they can process a lot more propellant per unit time. So you get a lot more thrust out of them. So if you had a nuclear reactor and at the start of your journey, you used it as a nuclear thermal rocket to get up to speed and then turned it into a magnetoplasmadynamic, you put the power to the magnetoplasmadynamic thrusters. So you continue accelerating more slowly during your journey. Now you're getting somewhere a lot faster. So that's the reason that magnetoplasmadynamic thrusters are a lot, they're both efficient and they have a reasonably high thrust. And if you combine that with a good power source like nuclear, a nuclear reactor that you could use for both nuclear thermal high thrust needs, and then you could have your high efficiency thrust on your way there. So that would be sort of the optimal rocket engine. You could use solar if you're going to try to put things on Venus or Mercury. And Mercury's actually got ice on it and everything too at the poles. So it's not a bad choice. It's just harder to get to. So that's why the magnetoplasmadynamic thrusters will be so important for space travel. Oh, I think you're muted, Jibe.
Oh yeah, apologies. I muted myself earlier because there was some noise in my neighbor, and yeah, I was just talking about. Thank you so much for sharing so much information about this topic, and I think there are more you want to talk about, but is that okay that I ask some questions that I gathered?
Absolutely.
Yeah, I think you talked briefly about like related to this question, some information you've already talked about earlier, but maybe it'd be great to elaborate a bit more. So the question is, in terms of real world scenarios, what are the key challenges that space tech innovators face when working with magnetoplasmadynamic thrusters and magnetoshell technology?
With both of them is your power source. How are you going to power these devices? If I had a fusion reactor that gave me 10 megawatts of power and it was an aneutronic fusion reactor. So it's not making any dangerous radiation. This is not impossible. Lithium proton fusion works, helium-3 fusion works. There's a lot of helium-3 on the moon. So let's say we have an aneutronic fusion reactor. I could build something the size of a large SUV and I could fly the thing to the moon and fly back with one load of propellant if I had that much power. So the biggest problem right now is getting an efficient power source, a compact, efficient power source. Most nuclear reactors are massive. To make them small is difficult. The RTG energy sources, like you see the rovers on Mars using, they're not very efficient, and they're using very expensive and hard to get, like uranium or plutonium. Fusion reactors using lithium and hydrogen, well, those are just common elements. So if we can get those to work and you have a good energy source, then that would completely, you probably wouldn't see chemical engines around much, except just, as the first, to get you off the planet, but you wouldn't see them used in space if we had a good power source to let us use magnetoplasmadynamic thrusters.
Awesome. Thank you for elaborating more on that. There's another question. I think it is a good time to ask the question. The question is, when we talk about reentry in the context of magnetoplasmadynamic thrusters,
Yes.
what are the key considerations?
Okay, let's talk about that. So one neat thing about having the power to power your magnetoplasmadynamic thrusters and your superconducting magnetic fields is that you can make those fields very, very big around your ship. And the thruster is putting out ions. So we're coming back from the moon in our advanced spaceship. And our advanced spaceship does not even have a heat shield on it. Okay. So it's made of a fairly strong metal. Maybe it's aluminum. That might not be strong enough. So it's coming back, and we power up our magnet, our superconducting magnet, and we generate a huge electromagnetic field, maybe 100 meters across. And then we start firing our plasma engine. Well, as we're firing that plasma, it is caught in that magnetic field, and it forms a bubble, right, of plasma around our ship. So now our ship is coming back, but it's surrounded by a 100-meter diameter bubble of plasma. When that plasma strikes the very start of the Earth's atmosphere, it's going to cushion our impact and slow us down. Think of the difference between a steel ball falling into water and how fast it hits the bottom, and a beach ball. Well, the beach ball actually never falls. It just floats on the top, right? So, and if you were to drop a bowling ball, it would fall slower than a steel ball. So we have this huge plasma shield that impacts the very top of the atmosphere and starts slowing us down before we even get to the thick part. And by the time we get to the thick part, we've come down like a balloon. We're going so slow that we really don't have much of a problem at all. You could maintain this until you reached a slow enough velocity that then you could just land normally. So you've got a force field, a plasma shield around your ship. And these engines, any of the ion engines produce these ions, and that allows the magnetic field to grab it and hang on to it. Now, if you do go fast enough that your shield is generating a plasma in the atmosphere, right? That plasma itself is going to be grabbed by that magnetic field, and it will reinforce your shield. So any plasma generated by contact with the atmosphere will reinforce your shield and make it even stronger. So that is a Magnetoshell, and the same company in Germany is the only one I know working on them. And it's Magnetoshell reentry shield. So those things will be possible and absolutely vital to future space use. There will be no reason to have a giant shield that burns away the way we do now, and then have to replace it every time. You won't have to do that.
Got it. Thank you. Yeah, I think shockwave is also an important subset in the topic when we talk about magnetoplasmadynamic thrusters. Could you please talk a bit more about what happens during a shockwave in the
Re-enter the
context?
atmosphere with a regular spaceship. As the ship is coming in, of course, we use blunt ones now. As they're coming in, there is a stagnation layer. There's a layer of air that doesn't move. Right outside that, you have a shock wave forms from the compression of the atmosphere. Because we're compressing a gas, we generate heat, right? And this temperature can get up very high, like 3,000 Kelvin. It gets up as high as a rocket engine. We're protected from that by that stagnation layer. So the kinetic energy is not transmitting through to your ship, but the photons of infrared energy are. So we get about 1,650 degrees centigrade heat on our ship. So our ship has to be able to survive that, to get rid of that heat. Now, there's several ways to do this. Of course, you've got a regular heat shield that burns away, right? And that's what the Apollo heat shields did. That's what the Orion does. That's what the Dragon capsule does. That's what Soyuz does. They burn away to carry away that heat. Well, for a reusable ship, that's not very useful. Those are very expensive. If they have a problem, it's not good. And so that shock wave is plasma, right? If you have a strong magnet in your ship, you can push the shock wave further out. And the flux or power of the radiated energy that is striking your ship gets cut in half when you double the distance, right? So if you double the distance, you cut to 1/4 the amount of radiated energy that's striking the surface. So the further you can push it out, the better. So you could use your superconducting magnet to create a magnetic field to push the shock wave away from the ship and reduce the temperature you have to deal with. So right now, the SpaceX boosters, they fire their engines when they come in. So they push the shock wave away with their rocket engines. And that's worked effectively too. It's called hypersonic retropulsion. So that's kind of a neat thing. They protect themselves from the heat by using their engines to push the heat further away. We would be doing the same thing, but we would be using a magnetic field to do it. And by generating our own ions and by using the ions generated in the air, then we can push that away and help protect ourselves.
Got it. Thank you so much for telling us more about the shockwave and how some solutions deal with the heat, how we protect the ship from the heat. Thanks so much. Yeah, I think next I'd also want to hear your insights on methane. Like, how is methane effectively utilized as a fuel source for power generation within this context?
So methane, the first American rocket scientist that really started running the equations was Robert Goddard. And way back in like the 1920s, Robert Goddard did the calculations and said, hey, you know what would work great as a rocket fuel? It would be methane, but it was expensive at that time and hard to get. And of course, it has to be stored cold. So with rocket fuels, you've got two sides. The density of the rocket fuel, the energy density, and the physical density, right? So hydrogen fuel produces a lot of energy, okay? But even though hydrogen fuel produces a lot of energy, it doesn't have a lot of physical density. So every cubic meter of hydrogen fuel weighs 71 kilograms. So we're talking about the mass you can put through your engine determines your thrust, right? Well, 71 kilograms per cubic meter. Compare that to, say, the liquid oxygen, which is 1,250 kilograms per cubic meter. And RP1, like kerosene, is 1,000, right at 1,000 kilograms per cubic meter. So to get the same, even though, say, let's say hydrogen is twice as efficient as your kerosene, right? But you're going to have to pump 5 cubic meters of your hydrogen for every 1 cubic meter of your RP1, of your kerosene. And that's why a lot of rockets still use kerosene or RP1 for their first stage, because the first stage is all about power. Second and third stages, efficiency is more important. So quite often, well, let's look at the Saturn V rocket. Made it to the moon, right? You've got kerosene or RP1 in the first stage, and then hydrogen in the second and third stages. Because the first stage is all about power. It's about getting those second and third stages up to enough speed and a high enough altitude that they don't have to worry about the atmosphere anymore. Just get them above the atmosphere and get them going about 2.5 kilometers per second. Then they launch from that point. Now it's you don't have to. When the tanks are hydrogen from the first launch, you get those giant orange things like the space shuttle has, and like the SLS has. That's not optimal. The Saturn V was a much better design in many ways. So you've got to worry about the energy density and the physical density. And as you look at hydrogen and you look at kerosene and you start working in and saying what has the optimum energy density and the optimum physical density, it turns out to be methane. So methane and liquid oxygen can be stored at the same temperature. So you can use a common dome. You don't have to insulate them. Because they're about the same physical density, your turbopump can pump both at the same time, right? Otherwise, if you've got a hydrogen oxygen turbopump, the hydrogen side is going to need to be this big and the oxygen side that big. Well, that's kind of a weird way to make a turbopump. So usually you have 2 turbopumps in a hydrogen engine. I like the Space Shuttle main engine. It had a low pressure fuel pump, a high pressure fuel pump, then a low pressure oxidizer and a high pressure oxidizer. But the oxygen pump was a lot smaller than the hydrogen pump. And the hydrogen pump had to spin at 35,000 RPMs. That's really fast. To put that in perspective, the Raptor methane pump only has to spin at 12,000 RPMs. Now, the faster you're rotating, the more the external stresses are on the outside of your turbopump. When turbopump blades break, that's when you get engine explosions. And there was an Antares engine that was going up and it exploded. You can see what that will do. One of the big problems Blue Origin is having with their BE4 methane engine is that they're going with 1 turbopump and it's having to spin really, really fast for that big engine. Now, SpaceX went with 2 turbopumps, 1 for the oxygen, 1 for the methane. And even though it's more complicated, it looks like it's going to be a better solution to that. So methane is the optimum between high efficiency and high power, energy density and physical density. Everything comes down to methane. Even when you look at propane and butane, and they're not better than methane. And methane burns clean. That means you fire your engine up and you turn him off and you get somewhere and you fire him up again and he's just fine. When you're using kerosene, like the Merlin engines that SpaceX uses, they have to refurbish them. They have to run like liquid nitrogen through them and everything to try to clean them out before they can use them again, because there's carbon that builds up, carbon byproducts, so polymerization. So you don't get that with hydrogen rocket engines and you don't get it with methane.
Got it. Thank you for the detailed explanation. That definitely makes a lot of sense for us to consider methane as a source of fuel. And I think that's all from the questions we've collected from our community earlier. But I have 2 more questions from myself. I'll ask you while we have you here. My first question is, apart from magnetoplasmadynamic thrusters, as we look into the future of space exploration, what emerging technologies or trends do you find most exciting and promising?
When we talk
like in
about
general?
space exploration in general, what benefit is there going into space? For every dollar spent on the Apollo program, $7 to $12 was returned to the American economy. When you get sick and go to the hospital and they put the monitoring on you so that the doctors can watch your vital signs through telemetry, that was developed for the Apollo program. Also in space, we can make things that we can't make here. We can make medicines that are pure. We can print organs. So right now we can make stem cells and we can 3D print an organ on Earth, but the gravity of Earth collapses the gel and mushes it all up before it can develop strong enough to survive on its own. But you can go into orbit and you can 3D print a heart and you can let those stem cells become what they need to be. And you could send that organ back down. So that's going to be huge in space, will be 3D printed organs. Right now, tens of thousands, hundreds of thousands of people around the world are dying because they can't get kidneys, they can't get livers, they can't get hearts. These will be printed in space from your own stem cells. So we'll take your stem cells into space, generate a new heart, bring it back down, and when it's implanted, you don't need all those drugs to keep you from rejecting it, right? You don't need to suppress your immune system. It is your heart. It is your tissue. It'll be young. And so we'll be able to do that with kidneys, livers, hearts. That's a huge plus. Also, when we get access to the moon, a lot of people, the moon's surface, the regolith is mainly aluminum and some titanium and stuff like that, basalt, former rock, stuff like that. And people say, well, that's not that exciting. Every crater on the moon was caused by an asteroid impact, right? A meteor, well, it's not a meteor because there's no atmosphere. But anyway, but by an impact. And every one of those craters, there's metal down in there, gold, platinum, heavy elements, right? As a matter of fact, in the Icon Basin, there is something so big and massive that it distorts its gravity effect, pulls satellites down when they go over it. So we can mine just under the surface of the moon, get to this big chunk of heavy metallic asteroid buried there. And we don't have to go all the way out to Psyche. That thing's going to have gold, platinum, and also iridium and things like osmium. All of the osmium on the Earth would not fill this room I'm in. But the osmium is denser than lead and in some ways stronger than steel. There's all kinds of alloys we'll be able to make that we can't imagine right now, because there are things we can't mix on Earth because of the gravity that we'll be able to mix in space. But there's also rare elements that are rare here that are common in space. All of the iridium in your ink pens, the little roller ball on your ink pen is iridium because it doesn't wear away. All of that is from asteroid impacts. All the gold on Earth is from asteroid impacts, because all those heavy elements sunk to the core when the Earth was molten. So every gold ring somebody is wearing is from space. And when we get out there and start mining the moon, we will find that buried under the surface, some were vaporized, but buried under the surface of the big ones will be these chunks of heavy metal that we can mine. And we know there's a really big one at the Icon Basin. So everyone's excited about Shackleton Crater and the South Pole and the North Pole and getting that ice that's there, and that's very important. But the big gold rush will come when we have enough infrastructure to mine the Icon Basin, because even if it's just an iron meteor, being able to make steel on the moon and make ships the size of cruise ships, we can lift with the rocket engines we have today. We can lift something the size of a battleship off the surface of the moon. We could never do that off the Earth with what we've got, but we can do it on the moon. So we've got water, so we've got hydrogen and oxygen. We could use engines like the RS-68s, and there you go. We could lift this massive spaceship with parts of it spinning for artificial gravity, with enough shielding to protect people from radiation. Because the first people on the moon and Mars will be 50 or older. They will have to be able to tolerate the radiation without, causing themselves without shortening their lifespan. right? The 20 and 30-year-olds can come later once the founders have built the shielded environments. So when our ships can be big enough to be shielded and our habitats are shielded, then the young people come.
Thank you. All sounds very exciting. That's why we firmly believe that this space 2.0 era, there's so much potential about it, and it's all very exciting, and we're very looking forward to the innovative solutions coming to existence in the future. Yeah, I think it's a good time to wrap up now. Thank you so much, Joseph, for joining us today and presenting this great workshop. I really appreciate it. And yeah, before we wrap up, I just want to say once again that our Starship Use Cases Hackathon submission portal is already open. We have prepared a prize pool of $100,000. And we thoughtfully designed 18 use cases and 2 open challenges for all the audience. If you're a hacker or want to be a hacker to tackle, we're very excited to have launched this hackathon program, and we can't wait to review all of your submissions with innovative solutions for space. We encourage everyone who has a passion for space to join us and shape the future of space exploration. And if you want to learn more about this hackathon program or DoraHacks in general, please feel free to click the link in the description to the hackathon page. Visit our website at dorahacks.io. And we do have more space-related live sessions in the pipeline for you. Make sure to follow us on YouTube and Twitter at DoraHacks so you won't miss out on any of the upcoming workshops and project demo sessions we're about to host. And one more thing I want to mention, that if you guys want to learn more about space, go check out Terran Space Academy as well. They have, like Joseph has presented so many great videos. I learned a lot from the videos. So definitely go check out, or if you want to reach out to Joseph, please feel free to check out Terran Space Academy and leave comment, just interact with Joseph. Yeah, with that being said, I want to say thank you to Joseph once again for being here with us today, presenting this great workshop. Really appreciate your time. And I want to say thank you to all the audience for tuning in today. We will see you soon. Have a great one, everyone.
Thank you so much.
Bye-bye.
Have a great day.